One of the things when we're working with acids and bases is using one against the other to figure out concentrations or to neutralize or whatever. So we have a couple different scenarios of how to figure out the math behind neutralizing acids and bases. So if we take a look at this first example, we see a classic type of question. It's asking how many milliliters of a specific acid are needed to neutralize another known set of quantity and strength of a base. And you'll notice that here is your equation, okay? Your molarity times your volume times your number of hydrogen ions equals your molarity times your volume times your number of hydroxide ions. Now this looks very similar to other types of things that we've seen before when we're making dilutions and solutions and so on, M1, V1 and so on. So we're just kind of using the same concept. So let's take a look at sulfuric acid. Remember that is H2SO4, and we have sodium hydroxide, which is NaOH. Okay, so this is going to help to figure out the problem. We just pop in the numbers as they apply. Make sure your units agree, and they already do here. It doesn't have to be liters or milliliters, but make sure that the units do agree. Let's just pop in the numbers. So just taking a look in here, we're looking for our volume. So I don't care if this is going to be my M1 or V1, really, it's just keep track of your units here. So my molarity was a 0.5. We're solving for milliliters. I'm going to label it milliliters just to help out. And my number of hydrogen ions, well, we have to know that it's sulfuric acid. So that is 2 hydrogens in there to form hydrogen sulfate. Now, take a look at the other side of the equation, my base side. We see that we have a strength of 1.5 molar concentration. We have 1,600 milliliters. Now remember, the problem might try to trick you and say that we have 1.6 liters. If they're asking for milliliters here, get the units to agree. And then the last piece, we see that sodium hydroxide is NaOH, so we have 1 hydroxide present. So we get X by itself, and so to do that, we're going to just basically pull these two off to the other side, 0.5 times 2. Now remember, we don't multiply this and then write down our answer and then multiply this and write down our answer and then divide again. Keep it all in your calculator. 1.5 times 1,600 times 1 equals, divided by parentheses, 0.5 times 2. And we end up with an answer of 2,400 milliliters. Okay, now this makes sense because my base was it was 3 times stronger than my sulfuric acid. Even though I have more hydrogens than I have hydroxides in here, we're going to find that my answer should go up from there, and I have 2 significant figures. Now, we take a look at the next problem. We can use the same type of thing. Here we were asking, how much do you need? Here's another one where we can actually use the information to figure out how strong was the base. Okay, so we just pop in our equation, 275 milliliters. Okay, we don't know, here's my base, we don't know its strength, so I'm going to just pop that out in front here, and we see that it was calcium hydroxide. Now calcium hydroxide, you should know by now, is CaOH2. So we have 2 hydroxides. Now notice that even though the equation here says hydrogens, I just took the information that we started with, okay? Let's take a look now on the acid side. We had 3 molar concentration, and we said that it took 700 milliliters to get there. Okay, this is in milliliters as well. And then lastly, it's hydrochloric acid. Hydrochloric acid is HCl, so there's only 1 hydrogen present. So I'm getting X by itself, which means that I divide both sides by the product of 275 and 2. Again, take it in one session with your calculator to eliminate any other errors. 3 times 700 equals, divided by parentheses, 275 times 2. X equals 3.81 for my strength. Now if you want to get really technical, we have 1 significant figure here, so then we would call it, my base would be 4 molar concentration. Now, one lab that is a very classic one for using the same concept is something that we call a titration. And so the math is exactly that same problem. I'm not going to run through the numbers on there, but you're going to see the classic labs that are always present. We have a instrument called, it's like a volumetric pipette called a biuret or a burette, okay? So we fill it with a solution, either an acid or base solution, and down below we have an acid or a base, doesn't matter which one you have, but we want to be clear on what is actually down here. And so the concept is this: we take the opposite, the complement of that, and we drop it in, drop by drop, and we can figure out its volume as you go down, because these are graduated cylinders essentially, and we're going to need an indicator in there to tell us what it is. If this is an acid, we put our indicator in. Phenolphthalein is the indicator we typically use. We drop in some indicator in there. If this is an acid down here, the phenolphthalein won't do anything. However, we're going to add our base in here until we start to see pink, because if you remember, phenolphthalein turns pink in the presence of a base. Now, if this was a base down in here, we'd add our phenolphthalein and it would turn instantly pink. And so what we do is we drop our acid in until that pink goes away. Okay, so down in here usually we're trying to figure out how strong is this base or this acid, whatever is down in here. So we know our volume. We know the volume of the titrate that we're adding to it. We would know that because we just read it off of here, how much it took to get my indicator to turn color. We would know the concentration here, and we would use the same concept to figure out how much or what the concentration was. So it follows the second problem we just did. This is the scenario that we'd have with a titration though.